Sky's the limit. If you could create any code that you wanted to run your parts more efficiently, what would you do? Let us know in the comments. Now, chances are it is possible to do what you're thinking, but it's going to involve some custom macros and subprograms. Now, I think that these 6 codes form the backbone of advanced programming on Haas machines: M97, M98, Alias M, G65, G66, and Alias G. Now, I have lumped all of these codes together because they are related. They are all subprogram calls of one type or another. M97 internal subcalls are terrific when we need to run multiple parts. We can create subprograms with our code and call them up at each vice, part, or fixture location. Now, this code is a moneymaker. It cuts down on the number of tool changes, and by filling a table with parts, we can run lights out, getting a full run of parts after we hit the green button as we walk out the door at the end of the day. By using internal subs, all of our code, the M97 sub call, and all of our subprograms will fit into a single file, making it a clean and simple way to organize our programs. We will use M98 external subcalls for any chunk of code that might get used by different programs. Our M98 code can reach out and grab that external sub to simplify things for us. In this example, we are machining some bearing pockets into extrusions. If this were a common feature for us, we could put all of this code into its own subprogram and call it up from our main program at any XY location that needs this kind of pocket. O1.nc is our main program. O2.nc is our subprogram. If we really wanted to make this bearing pocket subprogram call easier for operators, we would take that subprogram and give it some kind of nickname, an alias to make it easier to remember and call up. Now, right on our control screen, we actually have an alias page where we can do just that. We renamed our subprogram 09000 and then enter 310 as our value, our alias M code name. Now, anytime we command an M310 in our program, this 09000 subprogram will be called, and the machine will mill out one of these bearing pockets for us at that XY location. This is super handy if you have repetitive features to make. M310, aka M98 P9000, aka our bearing pocket sub. A simple alias to make things easier. Like how we refer to Pablo, Diego, Jose, Francisco, de Pala, Juan, Nepo, Museno, Maria, de los Remedios, Cipriano, de la Santísima, Trinidad, Ruiz y Picasso, just as Picasso. Simpler, right? And that's what subprograms do for us. They are the simplicity on the other side of complexity. Powerful stuff. And if there was anything that you missed, if you didn't quite catch, in regards to M97, M98, and Alias M codes, that's okay. We've made entire videos on those topics. You can check them out. Now, right now, we get to show you how powerful macros are and all the things that we can do with them. While all of these codes are subprogram calls, some of them are really special. These codes on the right are macro calls. Macro calls can alter and adjust the behavior of our subprograms based on our inputs. Now, these macro calls are only part of the story though, just one piece of what are collectively known as macros. Now, when we talk about macros on CNC machines, we are really talking about these 3 things: macro subprogram calls, macro variables, and macro statements. We need to learn all of these together. They are interdependent. They rely on each other. Now, we're going to expand this outline for a minute, just a moment, so you can understand the scope that macros can take. Don't freak out. Macro subprogram calls, G65, G66, and Alias G codes, macro variables, local, global, and system, and all kinds of macro statements that we use to perform math and logical operations. That's a lot to take in, so let's roll things back a little bit and we'll look at an example where we can focus only on G65 macro calls local variables, and the assignment of those variables. Here is our job. We need to machine these parts to varying but exact lengths. They've been rough cut. They're all 1 inch tall and 2 inches wide. Now, our best shot at making sure that both ends clean up completely is to take an even amount off both sides. We don't want to be taking off a lot of material on one end and no material on the other. So we're going to set our G54X0 right on the center line of our part. In that way, we know that we're always going to take an even amount off both sides, and that's going to give us our best chance for the part to completely clean up both ends. Now, in the code, we will need our tool to move to the right of our 0 by our finished length divided by 2. We need the edge of our tool to be at the edge of our part, not the center of our tool. So we need to move over by an extra distance, our tool diameter divided by 2, our tool radius. We'll repeat this on the left side of our part. Again, we want our tool to move to x length divided by 2 plus diameter divided by 2. Our macro subprogram is going to need variable inputs for our part x length and our tool diameter in order for us to calculate all of this in our subprogram. We will use address code I to represent our part x length and address code D to represent our tool diameter. On a graphing calculator, we use parentheses to control our order of operations. On our control, parentheses are usually used for comments, so we use brackets instead of parentheses in all of our macro statements. On our left is our main program, which uses a G65 P51 to call up our O51.NC program. By entering our needed inputs into our G65 macro call, our subprogram will have all of the info it needs to update our toolpath and run this part. Now, when we ask to make a longer part, all we'll have to do is adjust a variable on our macro call, press cycle start, and we are machining. The macro subprogram makes all of our adjustments for us based on these inputs. This is very different than an M98 subprogram call. Those subprograms are written in stone. They are immovable, they're unchangeable, they're only good for one particular feature. And again, we want to make not one part at 7 inches. We might have to make an 8-inch part, 9-inch, 20-inch part. We have to be adaptable, adjustable. Check out this graphic. On the left, we have our main program. On the right is our subprogram. The way this works is our G65 drops off information, input variables, onto a local variable shelf, like our I value, I 7.0. Later on, when our subprogram is called, our subprogram is going to go to that exact same spot on the shelf. It's going to pick up that information and make use of it using macro statements and assignments. That's how a macro works. It's a two-step process. Our main program is delivering things to our local variable shelf, and our subprogram will go grab that information and make use of it in that subprogram call. Now, each one of these spots on our shelf has 2 different names. It has one name that's used by our G65 and a completely different name, a number actually, that's used by our subprogram. On the main side of our program, our G65, everything is an alphabetical letter. But on the subprogram side, it's a number. In this case, our G65 I value, that spot I, has a number. It's number 4, pound 4. In our main program, G65 I4 delivers the information to the shelf. In our subprogram, we make use of that information by calling up pound 4. It's the same spot, two-step process. Now, how do we know that D equals pound 7 or that I equals pound 4? Well, there's no real easy way to know this other than going to our alphabetic address table in our manual. They're all listed here for us. They show us that A is 1, B is 2, C is 3, D is 7, IJK are pound 4, pound 5, pound 6, and so on. Now, our actual local variable shelf can be found in the control under current commands, right here on our macro variable page. Here's our actual program, and as we single block through it, we can see those variables being populated as soon as that G65 subprogram call is reached. Now, it's important to understand that most alphabetic address codes on a G65 macro line are not what we are used to as CNC programmers. Let's look at just this particular F value, F50. Under normal circumstances, outside of a macro call, this would tell our tool to feed at 50 inches per minute. But what happens when an F50 is commanded on a G65 line? Well, nothing at all really, other than some information is being placed on a shelf. Now, this is fundamental to macro calls. Now, some of you eagle-eyed viewers, after having seen our local variable page and our alphabetic address table in the manual, are wondering why there are some gaps. There's some wonky things going on here that need to be explained. So let's go together into the macroverse where we explain some of this wonky behavior that we actually need to know. We cannot use letters G, L, N, O, or P as variables. That would create some conflicts. That's where these gaps are coming from. And it's only going to leave us with 21 usable local variables. Those are the basics of G65 macro calls and local variables. But there are more variables than just our local. We've got local variables, we've got global variables, and we have system variables. Our local variables are temporary, they are fleeting. If we reach an M30 or an M99 in a program, poof, they're gone. If we cycle power on the machine, they disappear. They are really only to be used when passing information from our G65 line to that local variable shelf. Now, if we go to the current commands macro page, next to those local variables, we are going to see our global variables. If we need to store or keep track of a local variable or any value, we should really be copying it into one of these global variables. Information is just more secure when stored in a global variable. Even if we cycle the power on a machine, we're not going to lose the values in those variables. Those variables can only be overwritten if you're actually doing it manually at the control or if you are writing over that value from within a program. They are secure. That's what they're there for. Now, that sound means we have some housekeeping to do. We are going back into the macroverse. On older classic Haas control machines, our global variables are 3-digit. On newer next generation controls, our global variables are 5-digit. Now, older 3-digit variables can still be used on newer NGC machines though. If we enter pound 100 equals 1 on an NGC machine, we would see it populate global variable 10,100. Pound 100 and pound 10,100 on an NGC machine are interchangeable. Now, we have hundreds of global variables available to us on both classic and NGC machines. Lots of available personal shelf space. Local variables are for macro subprograms. Global variables are for our stuff. We make use of those. System variables are tied to all kinds of machine, program, and system data. That's the machine's stuff, and we can access it. Just about every value on our offset pages have a system variable assigned to them, available for use in our macro calculations. We can access our settings. We can create our own programmable alarms by using our pound 3000 system variable to alarm out if that setting that we just checked wasn't how we wanted it. And just look at all of these system variables that we can play with. Look through your manual for the list that applies to your machine. Local, global, and system variables. These are the lifeblood of macros. Okay, let's go back and take a look at our list of advanced subprogram codes. These codes on the left are regular subprogram calls, fire and forget. The ones on the right are macro calls because they can pass variables to their subprograms. And by the way, macros is a paid option. If you have the probing system on your machine, you have the macros option. If you don't have probing, if you have not paid for the macros option, you can use these left codes. You cannot use the codes on the right. We talked about G65 macro calls and how they work with local variables. Now, a G66 macro call is very similar to the 65 that we looked at, with one big difference. G66 calls are basically custom modal CAN cycles that will run our custom subprogram at every location reached until we stop this behavior, canceling it with a G67 command. In this example, we created our own G66 drilling CAN cycle for extrusions. Our drill will feed through the top wall, rapid down through the empty middle space, and then feed through our lower wall before rapiding up and out. And because this is a macro, we can control for our drill depth, our extrusion wall thickness and height, our rapid plane, and our feed rate, all through the use of variables. A few minutes ago, we showed you how to program this part, cutting both ends using a G65 macro call. We can actually take that same macro subprogram and turn it into an Alias G code. Earlier we showed you an Alias M code. Those can't pass variables. We can create an Alias G code that can pass variables, the Picasso of G codes. If we take this 51.NC subprogram, rename it 9010.NC, we can give it its own alias name, like 311. Every time we command a G311 in our program, it's going to reach out and run that macro subprogram for us, an Alias G code. We made an entire video on aliasing G and M codes, and we will link to that in the description. At the beginning of this video, we said that macros was really an umbrella term that covered macro subprogram calls, macro variables, and macro statements. So what's a macro statement? A macro statement is really anything that is not standard basic G code. If we look at our outline again, we have an entire list of all the different macro statements that we could make, that we could use. The program that we wrote earlier actually used some math operations. We said pound 4 divided by 2 or pound 7 divided by 2. Those are macro statements. And we're not going to go through all of these. We'll make more videos on these and we'll link to them in the description, some that we've already made. I'm going to give you one example. A lot of times when we write macros, we have to make sure that our programs can run safely. And sometimes if an operator wrote G65, P whatever, and they did not fill in all of the variables, we could run into problems. If our subprogram pulled something off of a shelf and that shelf was empty, it could crash our program. A lot of times my subprograms, I'll write a macro statement to make sure that somebody wrote something to that shelf location. An if statement. If pound 4 equals pound 0, then pound 3000 equals 10. Alarm out. Pound 3000 is a macro statement that we can create our own alarm. Pound 0 is a really unique variable. It's not a regular local variable. It's not 1 through 33. Pound 0 is not a number, and you can see that in your manual. We use that as a way to tell if somebody forgot to put something on the shelf. If there was never anything put on that shelf in the G65 statement, then alarm out. If pound 7 equals pound 0, then alarm out. We do this all the time with these type of macro statements. We can also use these if statements to branch, take a program one direction or another. Endless macro statements. If you want a video on one of these in particular, let us know in the comments. In our G65 example earlier, we used address substitution, dropping in local variables in the place of our x coordinate. If our bar size wasn't always 1 by 2 inches, we could have created more variables for our part y and z dimensions and added those calculations to our program. This is just one of the many videos we've done that cover macro topics, and we have linked to those other videos and tons of bonus content in the description of this video. And let us know in the comments what you want to see next. If you've done something really cool with macros on your machine, let us know. We'd love to hear about it. Thanks for letting us be a part of your success and for watching this Haas Tip of the Day.
I don't feel like you need to do that one again. Do you feel like, I feel like you nailed it. I don't think it's fun.
I don't hear why we can do it again. I don't know why. Now I'm stuck on it doing it again. Use the last take, Frank, because this take's going to be worse. And we shouldn't be filming this at all right now, but we're going to do it anyhow because of some weird OCD.
Okay, go.
Or I can't stop myself. Here we go. Here we go. Now, if